This is section 2.7, analyzing graphs of functions and piecewise defined functions. We'll begin with testing for symmetry. So we'll consider an equation in the variables x and y. We will have symmetry with respect to the y-axis if we substitute opposite of x for x and we have an equivalent equation. If we substitute the opposite of y in for y and we get an equivalent equation, we have symmetry with respect to the x-axis. And substituting the opposite of x in for x and the opposite of y for y, and we get that equivalent equation, we have symmetry with respect to the origin. So let's just go ahead and check each one of these. We'll begin with symmetry with respect to the y-axis. And we're going to have y equals the opposite of x cubed, and that's equal to the opposite of x all cubed. So this is a no, because that is not our original or equivalent equation to what we started with. Okay, now x-axis, and you can see above, for symmetry with respect to the x-axis, to test that, we replace y with a negative y, and as you can see, we end up with y equals the opposite of x cubed. That's also a no, that's not what we started with. And now we'll test symmetry with respect to the origin. And we're going to replace y with negative y and x with negative x. So we end up with the opposite of y equals negative x cubed. And of course, multiplying both sides by a negative 1, we end up with an equivalent equation to what we started with. So this is a yes. Okay, let's do that for number 2. We have the y-axis. Y is equal to the opposite of x, all squared plus 5. And that's equal to x squared plus 5, and that's a yes. For symmetry with respect to the x-axis, we will test with the opposite of y equals x squared plus 5, and that leads us to y is equal to the opposite of x squared minus 5, and that is not what we started with. And with respect to the origin, we will replace y with negative y, x with negative x, and see what we come up with. And that is a no. Okay, and let me highlight this yes with what we had, okay? Okay, number 3, let's check for the symmetry with respect to the y-axis. We'll have the opposite, that's when we replace x with negative x. And we end up with x squared plus y plus 1 squared equals 4, and that's exactly what we started with. X-axis, we will replace y with negative y. And that's definitely a no. That's not going to happen. And I think that I should not have put that there. Just replacing y with negative y. Sorry about that. And then the origin is when we replace both of them. Actually, I did that in the previous check. And that comes out to be x squared plus, and you could even switch this around. You could say 1 minus y all squared, but that's again a no. So we are symmetric with respect to the y-axis only. And in number 4, let's check with symmetry with respect to the y-axis. And here we'll replace x with negative x. And taking the absolute value, I end up with, I could just write to the right, and that is a yes. That is what we started with. Okay, and symmetry with respect to the x-axis, and here we'll replace y with negative y, and then we have y equals the opposite of the absolute value of x plus 2, and that's a no. And the origin will replace y with the opposite of y, x with the opposite of x, and see what we come up with. And that's a no. Okay. So those were 4 really good examples on checking for symmetry. And now we're going to talk about even and odd functions. Very, very similar process to this. We will first check and see if we have an even function or an odd function by doing the same thing. We will find f of the opposite of x. And if we have our original function, after we plug that in and simplify, plug a negative x and simplify, we will be symmetric with respect to the y-axis. If we replace x with the opposite of x and we come up with the opposite of what we started with, we will have symmetry with respect to the origin, okay? And if neither of those are the cases, we will write neither. So it has to be even, odd, or neither. So let's begin with number 5, and we're going to go ahead and just plug in the opposite of x. And as you can see, we actually have what we started with. So therefore, we have an even function. That was this first case. Okay, let's look at number 6. We have f of the opposite of x all cubed, opposite of x plus 3. And now simplifying, we have negative x cubed plus x plus 3. Definitely not even. Now, let's try to simplify a little further and see if we can come up with the opposite of what we started with. So you could factor out, we could say what the opposite of f of x is, and that is, actually let me change that color. So we could say that the opposite of f of x up here, that would be multiplying both sides by a negative, is the opposite of x cubed plus x minus 3. And that is definitely not equal to what we came up with. You can see we have a plus and we have a minus. Let me do that in yellow. So we are not odd either. And so now we can write therefore neither. Okay. Now in number 7, we'll go ahead and take f of negative x. We come up with the opposite of x cubed plus x. So we're definitely not even. Let's go ahead and see what the opposite of f of x is. And that's the opposite of x cubed plus x. And actually, that's what we got. That is actually equal to f of negative x. Therefore, we are odd. So this is equal to f of negative x. So we have an odd function. Okay, looking at this next set of work, we see we're going to graph piecewise defined functions. And basically, a piecewise defined function is a graph defined in pieces. Okay, so there's a piece of the graph that is has x values that are less than 0 and another piece that's greater than 0. Let's first take a look at this graph. As you can see, it is the left side of a parabola with an open point because we have less than 0. X squared plus 1 is a parabola that opens up. And we only want the x values that are negative graphed. Then we have a line, f of x equals x minus 1 for any x values that are greater than or equal to 0. So equal to 0 and greater than. Let's go ahead and try to find some function values of these. So f of negative 1 says when x equals negative 1, what is y? That's what that means. Okay? And we'll do that for all 3 of these. So when x is negative 1, y is 2. Okay, f of 5. So if we can go to the graph, when x is 5, y is 4. Now, what could we also do? Take a look here. If we didn't have the graph, you would notice that negative 1 is an x value less than 0. So we would use x squared plus 1. So negative 1 squared plus 1, and that's equal to 2. So if we don't have the graph, we would use the function definition. Likewise, for f of 5, we would say that 5 is greater than or equal to 0. So we would use x minus 1. So 5 minus 1 is 4. Okay? How about 0? Which piece does 0 fall in? Yes, 0 is greater than or equal to 0. So it would be x minus 1. Our x is 0. So we would have a negative 1. Let's see if that's on the graph. F of 0 is negative 1. Okay, what do you notice about number 11? We have no graph, so we have to use these intervals in order to decide which definition to use. Will we use the first one, the middle, or the last? And it all depends on where our x value is. So starting with h of 1, we can see that 1 is less than 2. So we will use x squared plus 3, which is 1 squared plus 3, which is 4. h of 3, 3 is between 2 and 4. So this is the one we will use. For this one, and that's simply equal to 7. For h of 4, again, we're going to be in this middle interval because 4 is less than or equal to 4. So we also have 7. And h of 5 is going to fall into this last interval because 5 is greater than 4. So we will have 2 times 5 minus 1, and that's equal to 9. And I probably should have written 2x minus 1. Okay? Now let's try to graph a piecewise defined function. Okay? So what we're going to do is we have two functions. We have y equals 1/2 x plus 1, and we have y equals the opposite of x minus 1. And let's just go ahead and make an xy table for these, and you'll be able to see these pretty well. So this first graph is when x is less than 2. So let's go ahead and use values that are less than 2. We can have maybe a 0. Let's actually put 2 on there and see where we'll have an open point, okay, at 2. And then we can use 1, or we could use 0, and we could use -2. How about that? Because those will fit well in the equations. And let's go ahead and plug those in now. So 1/2 of 2 is 1. 1 plus 1 is, when x is equal to 2, that's 1 plus 1, and we will have 2. And there's an open point there. I'll go ahead and highlight that. Okay, when x is 0, y is 1, and when x is -2, we have 0. So let's go ahead and place those on our graph. At 2, 2, we have an open circle, 0, 1, and then -2, 0, and we can connect these. And that is our piece where x is less than 2. Now, let's go ahead and make a table for our other graph. X is greater than or equal to 2. So we're going to need 2 here, and we're going to have a closed point. Okay, so that would be -2 minus 1. That would be -3. And I don't know, let's give some more values greater than or equal to 2. So we could use 3 and 4. So -3 minus 1 is a -4, and a -4 minus 1 is a -5. So placing these, we have 2, -3, and we're going to have a closed point, 3, -4, and 4, -5. And so the other part of the graph looks something like this. Okay, so you can see the function defined in pieces. Let's look at number 13. And again, we have a piecewise function. And we'll have 3 different graphs this time. And we'll just go ahead and write them down. We have y equal to -1. We have y equal to x minus 1. And y equal to -2x plus 6. We'll just choose some x and y values. And these first ones will be less than 0, but we'll go ahead and put 0 on there. And I will highlight this as our closed point. And less than 0, we'll go to -1 and maybe -2, okay? And plugging those in, every y value is -1. Y is always -1, okay? Let's look at this next one. Now we have 2 endpoints here. We have a 0. We'll let x be 1, and we have a 2. Now, these are going to be closed at both ends. So I'm going to use a green highlighter. How about that? Whoops. Since these are going to be closed at both of these places. Okay, and plugging those values in, we have -1, 0, and 1. Now, we need the x values greater than 2, so we'll start with 2, and I guess use 3 and 4. And again, we are going to have an open point at 2. And then plugging these values in, we have 2, 0, because -2 times 3 is -6, and -2. So let's go ahead and plot these. We have an open point at 0, -1, -1, -1. Would that have been a -2? Yes. And here you can see that y is always 1. Okay, -1. Okay, let's go to our next one. We have a closed point at 0, -1. So now I'm going to take this open point and make it closed. And then we have 1, 0, and 2, 1 is also closed. So this is our next piece. And our last graph, 2, 2, open, 3, 0, and 4, -2. And I think I put those in the right spot. 2, 2, 3, 0. Yep, I think it's just the way I drew that. And I didn't draw that very good. And it looks like that. Okay. Not real happy with these points here. See if I can do a better job. So 2, 2, 3, 0, and 4, -2. Maybe the grid is just not. There we go. That looks a little bit better. Okay. Now let's introduce the greatest integer function. And actually, we can use this on our calculator, but I think it's really important that we try this by hand. And basically, whatever the x value that is your input, we are going to try to find the greatest integer that is less than or equal to that x value. So let's go ahead and take a look at this first one. And sometimes it's easier to have a number line here. So if we have this number line, and maybe I should move that up here right in the center. And if we have 1.3 on our graph, the greatest integer that is less than or equal to 1.3 is going to be 1. Okay, let's put a -0.2 on our graph. And the greatest integer that is less than -0.2 is going to be a -1. Okay, how about a 5.6? The greatest integer that's less than or equal to 5.6 is going to be 5. And I'm sure you get this now, but the greatest integer of an integer is itself. Okay, so we're going to go ahead and try to graph this greatest integer function, the greatest integer of x minus 1. So let's just give a few values of x, but let's use intervals. And I'll write these over here. If x is between -1 and 0, then the greatest integer of x minus 1 has to be equal to negative 2. Okay? And we could do some test values. I might be able to do some test values over here. And that would be because, let's say we had x equal to negative 1. That would be the greatest integer of negative 2. And that would be negative 2. Okay? Because it would be itself. But if we had negative 0.5, and I'll just draw a little line here for this first interval, we'd have the greatest integer of negative 1.5, and again, it's equal to negative 2. So, at negative 2, when our x values are between negative 1 and 0, it will look like this. Now, the second we have 0 as an x value, so let's write our next interval. If 0 is less than or equal to x is less than 1, we will have the greatest integer of x minus 1. For any of those values, it's going to be negative 1. Okay? And we could try a few of those out in that table if you'd like. But let's go ahead and get this graphed. So now we are closed at 0 and open at 1. Whoops, I think I might have made that other one too big. So this should have been closed and open, closed and open. Okay. So now you can guess what the next interval will be. So if x is equal to 1 or greater than 1 but less than 2, we are going to have the greatest integer of x minus 1 is going to be 0. It will look like this. And as you can see, this is also called a step function. Okay, and you can already guess what the rest of the graph looks like, but we're just doing a few of these. Whoops. Then that greatest integer of any of those values minus 1 is going to equal 1. So it looks like this. And that's what it looks like. So let's take a look at number 16. A new job offer in sales promises a base salary of $3,000 a month. Once the salesperson reaches $50,000 in total sales, he earns his base salary plus a 4.3% commission on all sales of $50,000 or more. So we are going to write a piecewise defined function, and we're going to call it S of X to model the expected total monthly salary as a function of the amount of sales, okay? So the most important thing is we have X is equal to the amount of sales. So let's note here that when sales are less than $50,000, we only earn the base salary. Okay? But if when sales are greater than or equal to $50,000, they will earn the base salary plus commission. Okay. Okay. I'm really having a problem there. So let's go ahead and give that a try. We have S of X is equal to, and let's go ahead and write that first value down. We're just going to have that base salary of $3,000 if the amount of sales is less than $50,000. But they will earn $3,000 plus 0.043 times those sales minus $50,000. So these are the ones that are, this is the amount in excess of $50,000, okay? Because we've already been paid the $3,000 for up to $50,000. And that is going to be when X is greater than or equal to 50,000. Okay. And now let's talk about functions when they increase, decrease, and are constant, when they behave this way. And as you can see, an increasing function from left to right, it's going uphill from left to right. From left to right, if the graph is going downhill, we have a decreasing function. And the function is constant if it remains the same, if those y values remain the same. Here are the definitions if you'd like to read through those. It's written pretty nice. It basically says when x1 is less than x2, but the y value of x1 is greater than the y value of x2, we have a decreasing function. So the definitions are quite nice. So we're going to use interval notation to write the intervals over which the function is increasing, decreasing, and constant. So the first thing we're going to notice is that this function is increasing in those two places. So that would be negative infinity all the way to -2. We're going to just use parentheses. You may see brackets used there, but I think it's nicer to have that. And then there's that other interval, 2 to infinity. Now we are decreasing on this interval, and as you can see, that would be 0 to 2. We are using intervals of x. Let me write that here. Use intervals of x to describe where function is increasing, decreasing, and constant. We want to make sure we always use intervals of x. Okay, and as you can see, we are constant right here, and that would be from -2 to 0. Okay, do you see that there are no places where this function in number 18 is increasing? So you can write never or none. Decreasing, we have this interval, and this interval. So this function is always decreasing. And we do not have any places where this function is constant. Okay, so let's go ahead and talk about relative minima and maxima of a function. So that would mean in this little area, so in other words, in this little neighborhood, the highest point is called the relative max. And in this little neighborhood, the lowest point is called a relative min. So let's see if we can identify the relative max or min of these functions in these next few examples. So as you can see, we have a minimum here. So we can say that the point, that's a relative minimum. And so the point -2, -1 is the lowest point in a small interval surrounding x equals -2. Okay, so that's just in this little area, that's the smallest point. So at x equal to -2, the function has a relative minimum of -1. So this is your x value and this is your y value. Okay, let's see our next point. We have a highest point in this little area right here. So the point 1, 0, 0, 1, is the highest point in a small interval surrounding x equal to 0. So we can say that at x equal to 0, the function has a relative maximum of 1. Okay, let's look at the relative minima and maxima in number 20. I usually just like to highlight these little points. So there are minima, there are our minimums, and there's our maximum. So let's go ahead and write those down. So at x equal to -1, the function has a relative minimum of -2. At x equal to, and they want minimum again here, at x equal to 4, the function has a relative minimum of 0. Now, at x equal to 2, the function has a relative maximum of 3. Okay, what do you notice about this function? This function begins and it goes up, and just for a second it levels out, but it never decreases and just keeps going. So in this graph, there is no max or min. We call this an inflection point. And let's wait on that. So we don't have a place where the graph is the lowest point in a small interval. And that concludes this section.